know that we have gathered here for a very good industry expert session by Xperi. So we all know how metadata helps us in our day-to-day life, like what we want to watch, when and from where we can watch. So the title for the session is Metadata Matching Challenges and Techniques, and we have our speakers for the session, Mr. Neeraj Sharma and Mr. Ravi Krishna. So, Neeraj sir is the director at software engineer at Xperi and has a 26 plus years of experience in multimedia domain, streaming, and technologies. He's from NIT Hamirpur, ex Media Kind, Ericsson, IRDETO, and NDS. Also, our other speaker of the session, who is Ravi Krishna sir, he is the senior director software development at Xperi, and sir has several decades of experience in the software industry. He has worked on and managed all types of software systems, including embedded systems, multimedia, communication systems, data processing, servers, cloud, and client applications. Currently, he manages the Shared Application Engineering Services Group in Xperi, providing application software across all business verticals. So, over to both of you, sir. Thank you so much.
Thanks, Aditi, and welcome everyone. So I'm Ravi. I will start off by introducing ourselves, the company, broadly what we do, and then I will set the tone for the specific problem that we are going to discuss today around metadata matching. And then I will hand it off to my colleague Neeraj to take off from there. Neeraj, if you can go to the next slide. Yeah, let's go to the next slide. So I won't go into great detail about what we do as a company, but we work in a whole range of entertainment-related technologies. Now, entertainment in the audio sense, in the video sense, television, radio, we work in all these technologies. We have a bunch of very well-known international brands. For example, any of us who has any audio equipment at home is quite likely that it supports DTS, the DTS range of technologies. Similarly, any of us who have a set-top box at home that can record the TV program which is coming, well, who invented this whole concept of recording TV programs? It was TiVo. Yet another example is digital radio, where while here in India, we still have primarily analog radio, except for a few trials here and there, radio also has moved on to digital transmissions and reception, and we are one of the prime providers of that technology. So radio, television, audio, video, this range of technologies is what we work on. Now, one thing that's kind of common across all of these, whether you listen to a song on radio, which is audio, whether you watch a movie, a TV show, whether it's on a linear channel, whether it's on OTT, one thing that's common to all of these is metadata. What is metadata? What exactly is the matching problem in metadata? What is the range of possible techniques? What are the challenges? That's what this session is about. And I think I will hand it off to Neeraj to explain the problem statement further and then go into possible solutions. And as we continue, please feel free to type in questions into the chat window. And mostly we have reserved some time at the end for Q&A, but we will run through all the chat questions at that time. Thank you.
Right. Thanks, Ravi. So let's start with what is video metadata. I guess everybody is pretty much well aware of what video metadata is. We can see a couple of screenshots that we're showing on the screen. Pretty much everything that you see on a streaming app or in your guide data on set-top boxes, that's all metadata, right? It comprises of a lot of stuff. We have listed a few things that you can see: titles, cast and crew, release year, languages, ratings, and everything and anything except the actual audio video content. Rest all around is actually metadata. So next two slides, actually, we want to talk about, before we get into matching the main topic for today, let's just try to understand why is that important, what we're trying to solve here. So these two slides are pretty much connected, so I'll just sort of, going back and forth on these. So there are two main use cases that we are trying to address here. One, being a metadata provider, we have our, let's call it, reference data set for this session. So we want to keep expanding our data set. We want to have more and more new releases, movies, TV shows, and whatnot in the world, everything. And how does that happen? We get data from many sources. We have manual sources, we have web, we have content partners, and whatnot. Now, how do we get a new data? I get a data, I need to know whether I have it or not, right? And how do we know that? We actually match to figure out we don't have it, let's ingest, we have it, no need to ingest. That's one use case. Other use case for us is we are metadata providers. So people send us their, let's say, catalogs and say, give us the data for it. So how do we know whether we have data for an asset? We match and figure out we have it or we don't have it. So these are two top cases. We are just trying to address them here. And this slide is just to give you an idea the sheer volume of things. So we have millions of assets in our data set, hundreds and thousands of data comes in, gets matched. So just setting the background why matching becomes such an important thing and what are the different needs and challenges for it, which we are going to cover in the subsequent slides. So as I said, need for it, just two use cases predominantly that we just spoke about to enrich data for a given record that comes to us from our customers, and also to avoid creating duplicate data within our data set, right? Now, the requirements, and again, they're very high level. I'm not going to go that deep, but things like, we have to match the content against a reference data set. We could have multiple data sets, which means we can provide more than one ID for a given record. Just go with the flow for the minute. We'll cover some of these things later. And then, of course, time is very, very important. We are doing millions of matchings against millions of records. We can't take forever. We have SLAs with our customers where things have to go in certain amount of time. So matching time is pretty critical. We want to avoid doing things again and again. So we should have some methods to do that. Large data set, as I've said, it's in hundreds and thousands versus millions. We are looking at that sort of volumes. And ideally, the matching should be language agnostic. You should be able to match in not just in English, but in any language. So those are like very, very high level requirements. And moving further, so challenges are like the top two ones, as you see, they are kind of coming from your requirements itself. Huge volume and latency. We have to be very, very mindful of latency. Then just to paint a picture for you to understand what different challenges metadata brings, which probably as a normal user we don't really know, is when you have content in different languages. When I say different languages, I'm talking about metadata language here, not the actual spoken content within that particular asset. So usually, if you're in a different country, let's say in French-speaking country, of course, you might be watching in French, but the metadata also will be in French, right? So just to give those kind of examples here, we have same movie in different languages when the title is also different. For example, Modern Family and Famille Moderne becomes in French. We have different titles in the same language itself for the same movie, like the title variants as we see here, for Fast and Furious. In English, there are two titles, and so in Spanish, and these are some examples here. And there are cases where a same movie, same even in English, but is in two different countries, let's say US and UK, they may carry some of the different data as well. So it makes things complex. We should be able to identify they are talking about same movie, different movie, or they are variants of each other. They are, all that kind of stuff. It makes life a bit more difficult in the back end, which probably on the user or on the consumer side, they won't realize, but on the back end, this brings in a lot of challenges. And accuracy, well, let's see what accuracy is. This is one of the examples where we have a very animation for kids, Alice in Wonderland, And if there's another Alice in Wonderland, which is sort of X-rated comedy, we are not supposed to match this. If this movie comes in and this data goes out, you can imagine how bad would that look like. It can have serious issues. So we're just trying to paint the picture right now why matching is so important, volume, latency, and these kind of problems where you have multiple different movies with the same title, let's say, and we should be able to figure out which one we are looking at. And just to give some more flavor to their problems are like, see, there's a movie which is Dracula. It's appearing under romance movies. I mean, one would imagine it should be under horror or that kind of genre, but it's romance. And then another classic example is Citizen Kane is a classic of 1940s. It says 2020. It's okay as long as we are able to identify which movie they're talking about. And this all has to happen algorithmically per se. Manually, we can always look and tell, right? So with that, we have set the context, what matching is, needs, high-level requirements, few challenges. And again, as I said, there are tons of examples. We can't cover all of them here, just to give you an idea what kind of data we get. And they're very, very sparse data at times, trust me. So, well, next is how many ways we can address this problem. So obviously, you can always do manually, which is obvious. We can always look at two contents and I can say this is right or wrong. This is very expensive, time consuming. You need like huge number of folds to do that. Second would be someone might say, okay, you know what, let's have string comparisons and have a plain string comparison at some level and get it done. Well, again, it's not efficient for sure. You will see as we move along, we are talking about one asset against millions of assets to figure out where am I, whether I have it or not. And then there are more problems. We'll talk about them. Then some sort of matching algorithm, and that's what we're going to talk about in this session today. Obviously, machine learning is the new concept. We are utilizing machine learning in almost every facet now, and matching is no different. And then there's a hybrid model, which, well, it's not standalone, but any kind of algorithms or even machine learning, end of the day, the data is so dynamic, so changing that sometimes they can't just find the exact thing, however accurate they are. So we, in the end, for very small percentage, however it could be, we need some manual intervention to say, for this asset, well, I could find two assets in my ecosystem. I'm not sure which one is the right one. Those numbers should be very small, like percentage should be small, but then yes, algorithms have, or even machine learning has some limitations and manual interventions are needed. So that's like a hybrid model per se, which most of us actually end up using anyway. So this is the whole context so far. Where are the problems? Why do we need matching and different challenging needs? Just I want to say a couple of things here. What we're going to discuss today is about not as a matching algorithm as a whole. We're going to discuss a matching problem, which is a subset of this whole eco matching system per se. So it has got something called a pre-processing, where we do a lot of stuff to somehow make sure we don't load our matching systems more, which means let's not do same thing over and over again. If I've done some matching, let's say yesterday or 6 months back, we should be able to avoid rematching it per se. So, and then matching algorithm is also about matching a lot of stuff. For example, I can match a title. And imagine, let's say, example could be like Alice in Wonderland or the King Kong or Titanic. There are more than one movie made in the past. So we might have more than one Titanic in our ecosystem. If Titanic comes for matching, we will be able to find, let's say, 3 movies in our ecosystem. I'm just trying to make you understand the algorithm at a very high level. So when we have 3 movies, how do we know which one we are looking for? So we go and match multiple fields, not just the titles. So there is well, you can design your own algorithm that you want, but we do match a few of the fields. Could be, let's say, release year, director, cast and crew, and so on and so forth. And eventually, at every level, when something matches or does not match, we sort of score them, boost the scores, penalize the scores, and eventually, end of the day, we have a final score. And the example that I was taking, let's say we have 3 candidates for Titanic, we got 3 scores, and then usually we have, as I said, these algorithms are developed over a period of time. A lot of experience goes in, a lot of knowledge goes in. We have different thresholds, and well, let's say one is a clear winner of that. So that's our match. And there are times when the data is very bad, incoming data. Imagine someone says it's a Titanic. The cast is Leonardo DiCaprio, okay, but release year is 1950. That doesn't add well. It's not true, right? So in that case, we might be not able to find a clear winner. I'm just trying to paint a picture for you. So then that's where I said manual intervention might be needed. We'll say, okay, I've got 2 movies. None of them is a clear winner because they didn't cross our thresholds of matching per se, but then manually you can intervene and do something. But anyway, so that's about matching algorithm. And we are going to talk about only a limited over the core piece of matching. When we say match, how does that work? Not pre, not other stuff. So with that, should we move on or any questions? Oh, you good?
I will mute from.
Is that okay? But then,
Okay,
yeah.
now say.
yeah, that's fine.
This is awesome.
They can hear?
It's better? Great.
All right.
Ask the folks who are struggling. So
Oh,
I'll do that. You can go ahead.
all right, cool. So, all right. Let's move on to the real problem and what we are discussing today. So, matching. So, as I said, as we've seen so far, we are talking about matching. And when we say matching, in our world, let's say we call it phrase matching. So, a title is a phrase, director name is a phrase, a lot of also known as anything you can imagine of what phrase is. And we're going to talk about phrase matching. So when I say Titanic is matched to a Titanic, basically we found one phrase matched against, there are millions of movies. Each one is a phrase per se. We have to match them. Now, this whole technique that we're going to discuss is just how can we make it faster? That's the whole thing. I mean, you can do it by brute force method. Very simple way, but it's going to take you, it's very inefficient way of doing things. So here is what we are going to discuss at a high level, of course, is bigram matching. Now, if you see on the screen, what we do, we have a phrase called Seinfeld. This is it's a series, very well known, famous series. So what's bigrams? I think you guys know. So, Seinfeld becomes 7 bigrams in Seinfeld, SEEI, IN, and so forth. Now imagine an incoming record by chance has a spelling mistake and it says Seinfeld. Now we match, right? Like in string match, it would say failed. But in this case, we do bigram matching. And if you see clearly, it says, you can obviously see on the screen, there are total 7 bigrams and 5 of them have matched just by looking at it. And then we have some sort of matching score, which says total matched bigrams versus what total we had, and then find the score. In this case, it's 0.71. We can have some threshold. Imagine the threshold is 0.7 for argument's sake. We say it's a match. So again, we'll go deep into further down. But what we are trying to say here is we are not doing string comparisons. We are doing bigram matching. That's the technique we are using, bigrams. Now, another example, beginning of an end and end of beginning. Now, these are 2 entirely different programs, but bigrams will say matched. If you look at it, 13 of the 15 bigrams are actually the same because that's what bigrams are. So this is just to give you an idea what different kind of data comes in. Now, as I said, our first thing in our algorithm is to match the titles. If titles are not matching, there is no point in going anywhere else after that, right? So if I have million assets, and if I'm looking for Titanic in that, if I find 3 Titanics, I don't care for rest of the millions. I'm just going to work on those 3 and then go deep down and see which one is the right one, right? After title, I go to release year, cast and crew, and so on and so forth. So title is my first thing, obviously. You have to begin from some point, title. So in this case, as if you see, oh, this is matching, not really, because once we go further down, and we'll see these 2 are different movies because cast and crew would be different, release year, director, and whatnot. So we'll come to they're not the same, right? So this is so far we talked about bigrams, like how do we match? Now the question is, when we say 13 matched out of 15 or 5 matched out of 7, that is the crux. How to reach that 5 as quickly as we can. Now imagine just in your, if you could imagine, I have in our data set, let's say we have millions of movies and even more millions of phrases. Like each movie can have a few phrases, right? Tons of phrases on this side. And let's say if you get a few thousand records to come to matching, even they have, thousands of phrases now. Each phrase has to go and match against each. You can imagine the sheer volume of matching. We have to optimize it. It just can't work that way. We have decided we'll go bigram, but how to do it quicker, right? So this is a 3-step process, and these 2 slides again are interconnected. So I will sort of go back and forth in them. So what we do, our first phase is called normalization. Again, we learn from our experience over the years. So we and to make it, more optimized, let's not have capital letters. Let's match small letters per se. Remove all special characters like semicolons or hyphens and stuff like that, right? Normalize the data, then convert them into bigrams. Now, ideally, and or rather what we do is those bigrams are represented into integers. And we'll come to that how. Integers, bring them to a maths word, bring them to a, let's say, 0 and 1s, and in such a way that we can do some very fast in-memory operations, which are like, as some of you or most of you might already know, at assembly level, we have some instructions which are like 1-cycle instructions. They're super fast, the fastest possible. Use those kind of techniques and match them and figure out this match and this did not match. So I got 5 out of 7. That's the algorithm we are looking at how to match. So take your phrase, bigrams, convert them into some integers and match them using typical AND instructions and use some pop counts and get the score. How do we convert a bigram into an integer? Well, you can do in many ways per se, but one of the ways is, because one of the important things we said is algorithm should be language agnostic, let's say. So one of the way is doing it this way. So you take a language, let's talk about English. It has got 26 alphabets. Let's take about numbers, because we have a lot of numbers in titles, like, Fast and Furious 5 and, movies with sequels saying 2 or 3 and whatnot, right? Use them as you want, and spaces are always there. With this, we have 37 characters. We are talking only about English, and same thing is applicable for any language per se. Just choose the same method. With that, there are possible 1, 3, 3, 2 bigrams, right? Now, this is a constant set. This is not going to change, right? Now, what we do is all the phrases that we have are in system. We calculate bigrams for them. No problem. So far, so good. Now we know we'll stack them on a frequency distributed way, which means the most number of time a bigram appears, let's say that is at a 0 index. So take an example. Let's say AB comes the most frequently in our data set. Somehow AB is used a lot, A and B together. So that stays at index 0. And then so on and so forth could be, I don't know, Z9 might be the least used. So we just stack rank them. Now we have each bigram has got an index. Now we convert phrases. Now, a phrase, a Titanic, has become, or like Seinfeld, has become SEIN. These are the 7 bigrams. Now, each of this bigram has an index value now, as I just said. So use those index values. And then, again, I can't go beyond a point. This is sort of an IP for us. But then we have a schema in which when we convert a phrase into, a bit values, this is how something, it'll look like something like this. This is the made up data. There's no right data what you're seeing on the screen, but the Titanic appears like, a number of bigrams and a phrase ID and, their indexes, and they're further normalized. So it looks like an integer value at the end of it. Now, once you come here, now imagine you have each phrase in your system is represented in this manner. And now we have incoming Titanic, follows the same process. We'll also have pretty similar integer, let's say series of integers. Now we bring them into memory, match them, and boom, we get the score. Well, great. This is good. But is this sufficient? Not really, because sheer volume, we have millions of phrases on this site. And so we take one phrase. Am I going to go and match it against the entire data set? Not very efficient, right? So how can we reduce the number of matches or calculation of scores? Is, well, I think you guys can guess it. If I have a title or of a phrase, rather, incoming phrase, which is having, let's say, talk about Seinfeld, right? 7 bigrams. Does it make sense to compare a 7 bigrams title against 15 or 16 bigrams? Like could be Fast and Furious 5. Doesn't make sense. It will not pass. I mean, it will always fail. Even if we run that, run the whole matching, and the score will be very low, right? So what we do, we, again, with our experience, we have found a certain threshold. So let's say plus minus 5 bigrams. So if I have a 7 bigram incoming record that I want to match, let's match it against plus minus 5. So from 2 to 12, imagine. Now, which is, just imagine, if I just do that, my sheer, the set against which I have to match and calculate the score has shrunk significantly. And all that can actually fit into memory, and we can do all these operations in memory. And to, again, to aid that, how can we do? So when we generate our phrases, as I said in the beginning, we have our phrases, everything is stack ranked, everything is done. So all those are sort of chunked in, this is 2 bigram chunk, this is 3 bigram chunk, 4 bigram chunk, right? So when I want, okay, give me chunks from 2 to 12, I'll just load that data into memory, and we do this typical AND operations there, and get the value. So that's the technique we do. So this was like this algo was developed by one of our senior colleague, and it's been in production for about, I guess, 5-6 years, and it still works, seamlessly, pretty good. We are matching, we are able to handle all the volume so far without any headaches, to be honest. And so I guess that's the main thing. I'm just concluding again on this, like why matching is important. I think you understand it's very essential for us, very expensive operation. I think we look at the complexities of it, and then the way to optimize it, again, convert them into integer values, and then try to load only the relevant data, or the much smaller data set against which we compare. And
I think there's a screen sharing issue. Can you
something
share
is,
the screen?
Alrighty, hold on. Screen share.
Yeah.
This will stop the screen sharing. Do you want to continue? Let me redo it. Okay. Yep. All right. So this is as I was saying, so this is the whole essence of how do we do phrase matching. This is very, very critical piece in the matching algorithm. This is the first step, and it gets repeated for every phrase. And as I said in the beginning, algorithm is not just about that. We do lot many more matches, and there's lot many more weights and penalties, and that makes the whole thing, and there's a pre-processing and post-processing. We're not going to go there, but this is just about how do we, the core of matching is what we were just, discussing, and that's what we covered. And I think I'll hand over to Ravi. So this has, it can be expanded to other areas, and I think Ravi will probably take it from.
Sure.
Yeah.
Thanks a lot, Neeraj. If you could just go to the previous slide for a moment.
Yeah,
right?
yeah.
So let's recap what we just spoke about, right? So on one hand, we have a large database of video metadata, which means titles, names of cast members, names of crew members of a movie, of a TV show, of an episode of a TV show, right? Stuff like that. On one hand, we have a large database like this. On the other hand, we have a catalog of similar things coming from a different source, right? And we want to find out for each item in the catalog coming from the other source, which of these millions of items in my database matches it most closely, right? That's the crux of the problem that we discussed right now. And this is important because you launch your favorite OTT application and you see a bunch of items there, right? TV shows, episodes, stuff like that. And whatever information you see there, right? In which year it was released, who acted in it, right? The whole thing, right? All the other details. Even things like the actual description, the plot summary, all that is metadata. And if this matching process goes wrong, then the metadata would get picked up from the wrong source. And it's actually a major thing, right? For example, the Alice in Wonderland example that Neeraj shared, if the matching goes wrong, it's in some cases, it's almost disaster, right? So that's what makes this such a critical. I'm sorry, what happened to the screen sharing?
I guess something is.
Yeah. Can we take it back again? And if somebody else is sharing, can I please request them to unshare?
Yeah, I guess someone else was trying to share it. Okay. Yep. You're back.
Thanks. Yeah. So this is critical, right? If the match goes wrong, and for example, the wrong kind of content gets shown under the wrong category, it could be anywhere from a minor annoyance to a fairly major incident, right? So this is an absolutely critical thing, right? And these records, catalogs of new TV shows, new episodes keep coming on a daily basis, and it has to be done in near real time, right? That's the crux of what Neeraj spoke about, right? Now the question is, okay, fine. We develop algorithms which are very specific, which are very efficient, right? It has to be accurate and it has to be efficient at a large scale. So we develop these things, right? Well, this is good for video metadata. It's also good for audio metadata, right? You have songs, you have large online providers of streaming music. It's exactly the same problem statement, right? Except that the exact attributes of each record could be different, right? Well, almost any record would have a title, right? A movie has a title, a TV show has a title, an episode, well, quite often it has a title, right? Sometimes an episode might just be an episode number, but quite often it has a title, right? Just keep it, right? So, but if you look at a song, well, a song does not have an actor, right? List of actors is not suitable metadata for a song, but the singer is definitely a piece of metadata, right? And there could be other things which are song specific, right? So in different domains, we have different attributes of the records that we have, but the matching problem is similar, right? We are talking about semi-structured data here, right? The data does have some structure, right? For example, every record has a title, right? If it's a movie, every record matches a list of actors, right? It's like a many-to-many relationship, right? Between movies and actors, right? So there is structure to this. I'm sorry, we are having some trouble with screen sharing. I'm not sure who is
sharing the screen. Please,
but can I request anyone else to unshare their screen, please? Okay. Are you good?
Aditi,
Yeah,
can you identify, please?
it takes some time to appear there.
Right?
Sure, ma'am.
Aditi,
I'll
please
just check it.
identify who
Yeah,
is doing that, please.
sure,
Can
ma'am.
you? Yeah.
Yeah, I mean, I could very well
Uh,
take that as an
Yeah.
example of
Whosoever
metadata,
is
what we
doing
see
this,
on the
please
screen
don't
there,
do
right?
because it is
Yeah.
So it has a
this
title and it
session is
has
getting
a bunch of attributes, right? It has a release date and stuff. So I'm not sure why it's still not reflecting.
Let me reshare.
Yeah. So while Neeraj reshares, I'll continue, right? So these algorithms that
sir, can
we
I
develop for one such
hello?
domain, it's actually applicable with tweaks to other domains, right? So we ourselves work with audio and video metadata, right? So, it's directly applicable. But just to take a completely different domain, then if we go to the next slide.
Yes. Yeah.
So
Yeah.
let's consider, right? A very different domain. Now, we all buy stuff online, e-commerce, from different websites, from different e-commerce aggregators, right? Platforms. Now, let's say I'm looking for a certain item. Now, I know what I want, right? Well, in this particular case, it's an iPhone 15, right? Now, what I've shown here are information about the same entity or information about what I think is the same entity from two different e-commerce platforms. Now, let's say that one of them says 75,000 rupees and the other says 72,000 rupees. Well, obviously, I would like to go for the lowest one, right? But am I really sure that they are both the same item? Maybe one of them has, I don't know, headphones extra. Maybe one of them has more RAM, more storage. Am I really sure they're the same item? Well, as now you can see, right, the structure on the left side and the right side. It's not like obvious that it's the same thing, right? Now, as a human being, I pay attention, right? For example, if I look at how exactly the amount of storage is mentioned, this is what I mean by semi-structured data, right? Now, if you look at the title itself has the amount of storage. Now, the amount of storage is obviously an important attribute for a phone, right? And the title has this information. But that part is not structured. I don't have a clear thing, a field saying storage : 128 GB. I don't have that, right? It's semi-structured data, right? Now, if as a human being, I look at it, it's kind of obvious to me. But we are talking about doing this at large scale in close to real time. So it's not very obvious how to do this, right? Because every item, every metadata field better be the same. And only then we are comparing apples to apples. Otherwise, it's apples and oranges, right? So this topic of metadata matching on semi-structured textual data is a very generic one. What we covered here is some techniques that we use when it's specifically video or entertainment related data. But some of these things are generic. They can be expanded to cover other domains. And I think with that, we are at the end of our slides.
Yeah.
I think we can open for questions. It could be either in the chat window or it could be just audio questions, live questions.
Any
Sir,
questions?
I have got one doubt, sir.
You can type or speak as you like.
Please go
Am
ahead.
I audible, sir?
Yeah, you're audible for me.
So in the previous slide, sir, as you have shown that comparison between
We
apple
can't
to
hear.
apples.
It seems Gaurav is
Sorry, sir?
talking.
You need to increase the volume.
If someone is
Oh, okay.
talking, they are on
Okay.
mute.
Okay.
Just a second,
Ma'am,
just a second. Just a second, I'll let them know.
We are unable to hear if anybody is talking.
I'm going there, just a second.
Ankita is trying to talk, but
I think.
is it the volume?
Yeah, let's increase that.
But it should come from there, right?
No, because we are connected to this.
Increase the volume from
Yeah.
this one.
I have done.
Yeah.
Say something.
It will echo if you do it from here. Be careful.
hello.
Yes,
Yes.
we can hear you now. Please go ahead.
Yeah, sir, I'm asking, like in the previous slide, as you have shown us the comparison between two Apple smartphones, but basically, like what a normal person would think is that yes, it is of Apple company and the specifications are majorly same, like 128 GB and black, then basically what is the difference between these two, sir? Like I didn't understand that thing.
Yeah. So the thing is, now when you talk about a cell phone, let's take the cell phone example, right? Now, quite often you'll have a single model which differs in certain attributes, right? In the case of a cell phone, the attributes that could differ within the same model, right? Within, okay, let's take, okay, let's take even an iPhone, right? Within the same iPhone model, the things that could differ are the amount of RAM, the amount of storage, and possibly any accessories, right? For example, one vendor might charge a little bit more and give a headphone along with it. The other vendor might not do this, right? Now, when I see that one vendor is giving for, let's say, 75,000 rupees, and the other vendor is giving for 72,000 rupees, right? Now, if everything is equal, then it's obvious that I want to go for the lower price. But maybe everything is not equal, right? Maybe one of them has something, some bells and whistles extra, or maybe some feature is different. Now, this is generally not a big deal if we as people, as human beings, try, right? I mean, we look at all the attributes, we quickly make up our minds whether they're the same thing or not, and then figure out, does it make sense to go for the lower priced one, right? But now, if I want to do this in an algorithmic way, then it becomes trickier, right? Because we saw that example, right? The amount of storage was not mentioned in a very easy to programmatically access kind of manner, right? It was in a free text field. It was embedded in different parts. So how does an algorithm figure out that both of them have the same amount of storage, right? That's the question that we are dealing with, right?
Exactly.
Now, you could imagine, for example, that if you use the bigram technique that Neeraj spoke about, then it doesn't really matter where the substring 128 GB appears, right? Because those parts of the bigrams will match, right? So this is the way some of these techniques can actually help. Now, obviously, the algorithms we have for video metadata don't blindly translate to some other domain, right? They would need tweaks, they would need changes, they would need enhancements and so on. But the problem statement in a broad level is the same.
So as we said in the beginning, so bigram is just a matching of phrases that can be applied wherever you want typically. But then the algorithm is more than that, right? It reads and compares many more fields. That will change when you change your domain per se. But if you really want to go for phrase matching, bigrams can work pretty much anywhere. That's the sense that can be extended.
Thank you, sir.
Any more questions?
So I had a question.
Go ahead.
You talked about how in memory the bigram methodology is very efficient. So can you elaborate on how exactly efficient it is, and what are the other if you're aware of the other methodologies that are used to perform the exact same action? How does the bigram methodology exactly hold, how is it exactly better than the rest, and how does the efficiency compare?
So sure. I mean, again, it's a okay. So let's say we were talking about if you don't go bigram way, let's say, you want to go character by character, your matching set increases, your permutation increases, right? So if we have we said, right, that we take two bigrams, I mean, basically two set of alpha values, alphanumeric both, right? So we are reducing our set, and then we are trying to match. I mean, in memory, see, converting them to integer in memory is slightly different story, right? That's just to make it faster. You can always do it otherwise as well. It's still going to work. It's just going to take time, nothing else, right? And with this, when we do this, like say bigram way, as I said, see, the whole thing is connected. Then we can segregate things like as I was saying, we can always have 2 bigram file, 3 bigram file, 4 bigram files, and so on and so forth. We can always go and find a subset, a smaller subset, and we can always index them. As we said, it's a fixed set, right? For any given language where alphabets are fixed, obviously, then we have all the bigrams are also fixed. So see, again, if you look at the end of the day, we are not doing anything different. If end of the day, what we did, we found a phrase versus a phrase. As I said in the beginning, you can always do a string compare and say, okay, yeah, it works. Yes, it works. Obviously, it works. It's just how do you make it efficient? And this is not the only way. There could be multiple other ways, I'm sure, right? But we found this works really well, and we found so this, again, you reduce into bigrams, and then obviously you try to utilize the integer mathematical and operations, as we call them, very fast one. So it's a combination of these sets. You can reduce it, you can convert them, and reduce your set first from the whole big set. Am I able to make you understand?
Yes, sir. Just a follow-up, sir. So there are other methodologies like vectorizing data to compare them on a vector plane. I'm not exactly sure how those things work, but how do they compare with the bigram method? I want.
Well, I can't really say which one would be faster per se. Let's say I don't have, there's no, let's say, data in front of me. But as I said, see, this is not the only way to work, right? You may want to do something different. It's just that, so as I said, so when you want to look at the sheer volume of matching, the data that we have, millions of data sets, thousands of coming in every day, you also look at the efficiency and your infrastructure. You can't have tens of nodes running matching algorithm, right? Because that's not very efficient, again, from a cost perspective. I mean, to do R&D is one part, but when you actually productionize your solution in an organization, the cost is also very important, right? So given all that, so it's not just it's optimized from multiple angles. So this can run on, let's say, much lower number of systems with much lower RAM and still works seamlessly.
Got it, sir. Thank you.
We have a question in the chat. In fact, a couple of questions, right? Maybe I will take the first one, and Neeraj, you can take the second one, right? I'll take the one from Vignesh, right? It's a good question, right? The question is, when we are comparing videos, right? Let's say video content, why are we just doing it with metadata? Why not compare the video content itself, right? The data itself, right? It's a good question. And the answer is, in some sense, is a practical answer, right? The first thing is metadata by itself is a big thing, right? So there are companies like ours and others that purely deal with metadata, right? We have large aggregate data sets of metadata, as commercial offerings. We don't have the actual video data, right? Because, that's the difference, right? Now, video data is video data, right? There's content ownership and rights and things like that, right? Even when that video data actually gets streamed, it's under heavy DRM and encryption and stuff like that, right? So first of all, it's not always possible to even have that video data, right? Metadata is what often gets matched. The second part is the sheer computational complexity, right? I mean, if you consider a video, I mean, you get what, 30 frames a second, right? And that's like that many frames. Which frame of which video would you compare to which extent, or, so obviously we can have many techniques there, right? It's an interesting problem. There are other places where that would get applied for sure. But just to figure out whether an incoming catalog of 1,000 videos, to what extent it matches the 10 million items we have in our database, right? For that problem, no, we would not compare the actual video data. Because first of all, we would not have access to the data. And secondly, even if it was there, well, it would be computationally, just not tractable at this point. Right?
Yeah.
That's exactly the answer there.
Yep. Yeah. Just to add to that, so many people or customers, they will send us the data. They will not send us they will send us the metadata, not the data. So they will say, on this channel from 10 to 12, I'm broadcasting Titanic and some data for Titanic. I don't know, let's say title and release or something. And they want us to give them data back. They're not sharing the audio video file with us per se, right? So we just get the metadata and we give them enriched data back. Like, okay, for this record, we have tons of data. Please take it. That's the model. We as we said, they're not giving us audio video file per se. I mean, that will be more expensive to match probably a video to video, but anyway, I mean, the thing is we don't even have the access, let's say, to the actual content itself. There are different pipelines, by the way. I mean, the metadata flow through different pipeline, actual content flow through different pipeline, but short answer is, yeah, we don't have the access to data.
There's a question about bigrams.
Okay, yeah. How do assigning integer to each bigram makes processing faster? Can't we make bigrams as the basic unit of search? Didn't assigning integer add the process of coding and decoding? Well, I didn't understand when you say, can't we make bigrams as basic unit of search? So are you, again, if we are staying in that string compare sort of world where, see, everything is end of the day is getting matched in ones and zeros, right? If I say compare Titanic to Titanic, eventually it probably does, it converts to ASCII value of each alphabet and then try to compare. Let me know if I'm understanding what you're saying. So that string comparison will also work if it's just say, okay, take BI and figure out where is my BI. Yes, but then what is BI? Computer will probably understand it as an ASCII value converted into, byte or 2 bytes, depending on Unicodes, and then it'll come back and search. So point is, we are still doing the same thing end of the day. When we do, let's say, if I may say so, if I say string compare, it's very easy from a user perspective, very little load or very little work for me, but it's not efficient. So when we pack them, we convert them and give them, frequency distributor index values. We pack them in a way that they are more efficient, rather than just doing a string compare or giving them ASCII values. Eventually everything is integers end of the day.
Yeah, so I think to add to that, specific question of what about the overhead of the coding and decoding, right? Coding, encoding as integers and so on.
Right.
I guess that is something that is done once, but then the
Yes.
comparison itself using that, as Neeraj said, the single cycle machine operations, that is done an enormous number of times, and therefore the extra overhead of encoding it once.
Yeah, we do it
it's not-
once, correct.
not,
So we have, imagine our data set, we are calling it reference data sets. Imagine it has got, just for the argument's sake, has 20 million phrases. So all those 20 million phrases, we have done bigrams and converted them to integers and keep them ready in those files, 1 bigram file, 2 bigram files, and it's all done once. And then that data set, we don't upgrade every day or every minute. I mean, there is a frequency at which we update that data set. Let's not go down there. But point is, those are pre-calculated. Only thing we do on the fly is what comes in. What comes in as either to get ingested or to get for matching. Only for those phrases, we calculate these bigrams and signing integers on the fly and just match. Does that help?
Hopefully it does. There's a couple of other questions.
Okay.
Also.
Yes, sir. Thank you, sir.
All right, cool. Thank you. Why can't we compare two phrases character-wise instead of bigram matching? Just, well, again, a little bit of more further optimization, I would say. So if you want to calculate, let's say character-wise, if your permutation combinations might increase, then how to explain this? If you want the same technique, the way, I mean, again, as I said, each one is connected to each other. The way we are said, I want to go diagram wise, right? So if you say I want to go character wise, either you can go back to string mode and say, okay, find where is A, right? And then it'll be tricky. A is independent. I mean, diagram sort of, what I'm saying. If I say give me T in my ecosystem, you see what I'm saying? How do you convert them to values? You can put that way. You can. It's just not optimized. You can always do, like, as I said, the multiple ways of doing it. It's not that it's not gonna work, but it's not how do you find a T in this ecosystem if you just go character by character?
And to add to that, right, if you take an individual character, I mean, we all know that E is the most common letter in the English alphabet, right? Now, if I take, an incoming record, and here is my big database of records, and I say, each individual character, the matches are going to be too high,
Sure.
right? Almost, if there are 5 E's in my incoming string,
Yeah.
and, almost, I don't know, maybe not every title, but a large number of titles would have a large number of E's, right? So the matches are just too many, right? Bigrams cuts it down, right? And these are fairly standard techniques in text processing, right? Now you could look at larger n-grams, right? But then the number of such combinations becomes higher, and then that becomes more difficult, right, to manage, right? And also then the impact of spelling mistakes and stuff, starts impacting more, right? So bigrams is really a trade-off in that sense, right? To kind of narrow down the number of items that we have to search, right?
Yeah.
That's one more.
Thanks for the previous reply. Could you please shed some light on the few parameters on which you based your setting of bigram score threshold on? Based on, yeah, okay. Well, it's a typical, see, when you develop something, you look at the results and you see, okay, with this setting, I get, most of the time this is correct. Like, so for example, let's say 0.7 was our case. So when we do that, when you run your system in staging or in your QA environment, test environments, that's where we come to know, okay, with this, I found these 3 came out as wrong. Then you go back and check, okay, you know what, here is the problem. I think this, we might have to go a bit higher. Then you go a bit higher. So there is no straight answer here. It's just that you have to practice and try out and then see the results. At some point, you feel this is the local, I mean, this is like minima. I mean, nothing is perfect. This is the beauty of it. You try to increase something else, it improves in some situation, breaks in some other. So you have to find a balance that, okay, this seems to be the most optimum, not perfect, most optimum. And then rest of the fields in our algorithm and other matchings will help to further narrow down our results. So, I mean, there's no shortcut, put it that way.
There's one more about tools and libraries and stuff.
Oh, where?
This one?
What tools or libraries can I use to analyze bigrams in a given data? I will have to come back on this. I don't have anything that I can think of straight away. Tools, libraries. I don't know. I'll
Yeah, we can get back.
We can get back on this one.
I think we covered all the questions in chat.
Yeah, yeah. Okay.
Let's give another minute if anyone has any chat questions or live questions.
So founder of Bigram.
I'm not sure we know offhand, right?
No, I know.
But I'm sure it's a Wikipedia search away, so we can
yeah, right. Yeah.
do that. Yeah.
It's a well-known technique.
But it's a well-known technique.
Yeah.
Yeah, right. I think Vignesh has asked that same question, right? Which
Yeah,
we covered,
exactly.
I think, in an earlier answer, right? I know. We could go for longer engrams, right?
Yeah.
But for example, what Neeraj spoke about in terms of mapping bigrams to integers, right? Now, when you have bigrams, the number of possible bigrams is a certain number, right? Which you can
Yep.
obviously compute very easily,
Yep,
right?
yep.
The number of possible trigrams is a much larger number, right? So from a computational perspective, that has some implications, right?
Yeah.
On the flip side, how well does your technique deal with things like spelling mistakes, right? So that's again a trade-off between between how efficiently you match, how well you deal with the errors in the data, things like that, right?
Yep.
So it's a little bit of a practical thing, really, right?
Yep.
So bigrams has worked well for us, but yes, one can always do research on other techniques. That's a fair question.
Yep, yep. Bigram is more future oriented rather than present. I am not too sure if I understand what you meant by more future oriented. So bigrams are there for a while. I mean, it's a well-known technique. In fact, it's called n-grams as well. I mean, in different scenarios, people can use n-grams, but I'm not sure if I quite understand what you're saying, future oriented.
I mean, it's quite a present technique. I would
Yeah,
say
it's
around.
been there for a while already. So nothing per se futuristic today about it. I mean,
We can wrap now, Neeraj.
sure. Okay.
Thanks. I think,
It's already fine. Yeah.
on time. And if anyone has any, follow-on questions, you can always email us, and we can always have a
Uh,
sit.
Ma'am, a last note to you people. Hello,
Yeah.
Yeah, we can
am
hear
I
you.
audible?
Yes,
Yeah.
yes.
So, ma'am, first of all, thank you so much, and sir, thank you so much, both of you, for this great session. I mean, it was fabulous, and we look forward to seeing you in such more sessions in the future. And I would like to thank all the participants too for their engaging questions, and with a very good saying, that is, believe in yourself, and you're already like halfway there. So I would like to thank all of you, and I think if you want, sir, then we can end. Thank you so much.
Sure.
Thank you.
Thank you. Thank you, everyone.
Thank you all. Bye.
Bye-bye.
Sir?
Yes.